local chapters provide education, policy advocacy, and community engagement that accelerate Colorado towards a carbon-neutral future powered by 100% renewable energy. Founded in 1996, CREST is a statewide, nonpartisan 501c3 that is supported by our sustaining individual members, our business sponsors, as well as donations and grants. If you're interested in learning more, go to crest-energy.org. It's www.crest-energy.org to sign up for the newsletter, social media, and particularly our YouTube channel, where we have over 255 previously recorded videos of webinars that are pushing 9.4 million views. Really quick shout out to our Northern Colorado business sponsors, Sandbox Solar, Solaris Energy, Cooter Valley Rural Electric Association, and PRPA, and ProLift Rigging, which I think is out of my mind, so I consider them up here. Couple quick and upcoming announcements. This Thursday, September 26th, 7 p.m. in Golden, Colorado. This will be in person, but it should be live streamed. Again, you can go to the website and find out. Homeowner experiences with energy conservation, heat pumps, and rooftop solar. This is a part, we've been supporting the Metro Denver Green Homes Tour for 15 years because it used to be the ASA Solar Tour. And this is kind of a part of that. It's going to have several people. It's moderated by Mark Niblos of the National Renewable Energy Lab. Tuesday, October 15th, 6 p.m., Grid Enhancing Technologies. I'm going to have a cuter title for it. We have some folks from Line Vision Technologies. They're on Boulder. They do dynamic line ratings, but they're familiar with Grid Enhancing Technologies, which is going to allow us to overcome a lot of the transmission challenges. We've got a grid that's old, but it's also really poorly managed. So just using software and management techniques, we can actually get a lot out of it. And transmission, if you're following the big picture of renewables, that's a big constraint. Then coming back up here to Fort Collins, that'll be a webinar, so it's statewide. Thursday, November the 7th, 2 days after the good old election. You can join us at C0. Those of you who are not familiar, C0 is a local engineering firm that does a lot of startup work and sort of concept to commercialization for clean tech, carbonization technologies. And of course, the title is Engineering, Energy Transformation, and Innovation at C0. That'll be 5 to 8 p.m. That isn't published on the website. It's on our meetup, but I will be announcing that shortly. Really long. It's 5 to 8. Lots of time to network. Guy Babbitt is going to give a little talk on what they do, and then you're going to be able to tour the facility to see, just all the cool stuff. Actually real stuff, making things. You guys are making this. And then today's Thursday. It's Wednesday. Sorry, going to my scribbler. I had this one. Just confirmed this Wednesday, November the 13th. This will be a webinar. We're going to have Bryce Carter with Colorado Energy Office talk about the Colorado geothermal roadmap. And so they've got the roadmap. They also put forth funded a bunch of projects to look at everything from getting geothermal out of oil and gas boreholes to just doing, regular ground source geothermal district heating for campuses and schools and whatnot. So all of that, crest-energy.org. We're sure I have to after that event. Otherwise, I'm going to hand it over to Reza from CSU to talk about his research.
All right, thanks so much for the invitation. Good evening, everyone. And here, excited to discuss our research program, what we do at Colorado State University, and what our vision would be for decarbonizing the fuel and water industries by designing materials and systems that potentially could be impactful to decarbonize some of the hard-to-decarbonize industries in the couple of decades. So as you can see, we design these catalyst materials. We call them bifunctional catalyst materials. I'll discuss in this presentation why we call them bifunctional. So this is our lab, research lab at the Powerhouse Energy Campus. You might have visited the Powerhouse. It's part of the CSU Energy Institute, and this is our headquarters, essentially. My lab is located on the first floor. We do lots of cool projects with the teams, with talented team of researchers, very diverse background, material scientists. We are in mechanical engineering, but we have material scientists, chemical engineers, chemists, and also obviously mechanical engineers. Our program is, again, the projects are very diverse. We work on electrochemistry and photochemistry, and the goal is essentially how can we use cheap electrons, hopefully from solar and wind energy, or directly using sunlight, solar energy, to do some of the chemistries that we think currently is practiced by using fossil fuels. So we want to essentially decarbonize and eliminate these reliance on fossil fuels. But why are we doing this? So we look at the curve and the goal to get to net zero carbon economy by the next couple of decades. And a lot of focus on harvesting energy, renewable energy, harvesting solar and wind energy. But you look at this curve, in order to get to net zero in the next couple of decades, we really not only need to focus on power generation, which is slightly more than a quarter of carbon emissions, but we also need to look at transportation, industry, and buildings. These are all important in order to get to net zero carbon economy by, hopefully, in this curve shows 2070, and we are hoping even to get sooner than that. But a focus on industry and the technologies that you look at in order to get us to net zero carbon economy. Right now, more than 1/3 of those technologies are either at the early adoption or at the demonstration or large prototypes. So that's exciting because that means that most of the technologies we need to decarbonize these industries are not out there. So these researchers really need to work hard to develop these technologies in the next couple of years to hopefully contribute to decarbonization of our economy. So that's the goal we are pursuing at Colorado State, and my group is pursuing very diligently. And the reason that we cannot, most of you might ask, so why we don't use solar and wind energy just right away? So the reason is they're not like fossil fuels, they're intermittent. Right now we don't have any solar just because it's evening time. So the goal is to come up with a system similar to batteries to store that energy around the noontime when you have excess solar energy. You can store that, and during the nighttime, evening time, you get to home, you need power, you can use that energy that you stored and then again use it so that you don't run out of power. So this is the goal. And again, batteries are great, but vacuum temperature batteries for long-term energy storage, for not just for a couple of hours, but for a couple of days, couple of weeks, couple of months. Batteries' capital costs just exponentially go up. And we need something potentially similar to carbon-based fuels or fossil fuels that we can store them, we can keep them, and then we can burn them when we need them to generate power. And that's why we focus in our group on primarily how we can generate, how we can store those cheap electrons into fuels, into molecules that we can store. So that's the primary focus for the overarching goal of my research program. And we work on wide variety of fuels. I'll give a couple of examples in this presentation. We work on hydrogen production, we work on ammonia production, we work on carbon-based fuels, a wide variety of carbon-based fuels. Right now we have focused on methanol, just because we get interest from automotive industry. They want to, one of the promising fuels they're focusing on right now, especially the Caterpillar, our strategic partner at the powerhouse, is methanol. So this is an interesting fuel, and also it's interesting to think about it and look at it, how to produce that electrochemically or using electrons from renewable energy.
Try to use it. Yes.
So you look at the industry and all those different sectors within the industrial division. So if you look at the biggest chunk of this pie chart actually goes to bulk chemicals, around 20% or 29%. And you ask what are these chemicals that really they're carbon intensive, that at the same time they're very energy intensive. So ammonia is on the top of the list, ethylene and both of propylene, methanol, and some of these carbon-based chemicals and fuels down here. And then you look at the carbon emissions, you see ammonia gets its own axis. Just because if you plot ammonia on the same axis, all the chemicals would be near the axis and ammonia would be on the top. So it gets its own axis. That is that how intensive this industry is, and how should we think about to decarbonize the ammonia industry as one of the chemicals that produces the highest carbon, and also it's very energy intensive. So obviously we need a paradigm shift to move towards a more sustainable process to synthesize these chemicals while potentially electrifying and decarbonizing the chemical industry. And what's motivating us, what's the main driving force for this transition is the increase in the cost of renewable electricity. A couple of 2 decades ago, you tell me what was the cost of solar energy and wind energy, and now the Department of Energy just putting out reports that by 2030 we are hoping we get 2 cents per kilowatt hour from solar and wind energy, which is pretty exciting. So that means that we might be able to compete with carbon-based chemicals and fuelings, or the chemicals that are produced currently primarily by fossil feedstock in our process using renewable energy. So it's pretty exciting for chemical engineers to think about these type of problems that industry is facing. So for just quick example for ammonia synthesis process, you look at the left figure is the thermochemical process. Ammonia synthesis is currently driven by methane, natural gas. So you through the methane reforming process, you generate hydrogen. You emit obviously a lot of CO2. Then you take that hydrogen, combine that with nitrogen. Again, you need power because you have to run it in the thermochemical reactor, high pressure, high temperature, around 250 bar, 500 degrees C temperature. You have to combine nitrogen and hydrogen to generate ammonia. What we are hoping to achieve in our research is how can we replace thermochemical process with electrochemical process, and just using solar and wind energy, get those electrons and combine nitrogen. We're using just air and water to generate ammonia. So we don't is absolutely carbon free. We don't generate any carbon in this process, unlike the incumbent technology, which generates essentially 1.6 tons of CO2 per 1 ton of ammonia right now. So pretty significant problem to look at and solve. But at the same time, so this is one example. We got many different chemicals in the industry, and the question would be, do we want to electrify all these chemicals? And obviously the answer is not, because some of them are really, when you do an economic analysis, you realize that the cost is just not driving the researchers to map toward electrifying the whole chemical industry, but there are some chemicals that we can absolutely think we decarbonize, and one of them would be ammonia. So my research program, again, looks at the wide variety of feedstock. We look at water, nitrogen, wastewater, and the nitrogen sources in the wastewater. We are hoping to capture those nitrogen sources and turn it into useful fertilizers. And of course, CO2, how we can take CO2, run it into our electrochemical system and generate some of the carbon-based fuels that we are pretty much using in our modern lives. And so one of the goals here is we don't want to create the whole infrastructure. So we want to leverage our current infrastructure. And it's critical to be able to create or generate some of the fuels with very minimal change in our infrastructure. We can adopt those fuels and these technologies to generate those fuels. Right? And not only the system is important, but also the balance of plant. This is something that we are hoping to build at the Powerhouse Energy Campus. Not only the main system or electrochemical system or electrified system to generate fuel, but also the balance of plant, the separation, a storage system, and all those components that run with each main system, the key system that generates fuel. And eventually the goal is you brought these outside in the grid as, again, long-term energy storage system. There are a couple of systems that is in place. Unfortunately, we don't have a commercial system that can take these electrons from solar and wind energy and create fuels, except for hydrogen in some cases, but mainly I'm referring to ammonia or some carbon-based vehicles. This is the example of Powerhouse Energy Campus. If you visited, you might have seen this engines lab. 120 kilowatt electrolyzer is an electrolyzer that generates about 40 kilograms per day. At the Kobe's that we run this, we generate this, and then run it through our gas turbine using hydrogen fuel. So pretty exciting addition to our powerhouse capability and equipments that we run at the engines. So the focus of my team would be on primarily how we can screen different metals, because in the catalysis or in the catalytic reactions, you obviously have to start with the material. What type of material, what type of catalyst you want to use to accelerate the rate of these chemical reactions. And a lot of focus in our program is how do we synthesize, how do we discover, design, synthesize, and refine this catalyst synthesis process to help enhance the rate of catalytic reactions. For some of the reactions I have in the video circle for nitrogen conversion, nitrate conversion, CO2 transformation. And we also focus on designing electrochemical reactors so that those catalysts, we incorporate those into electrochemical reactor. And eventually we try to understand, use a lot of spectroscopic and microscopic techniques to understand what's happening in the reactor, what type of products you're producing, how can we improve based on the feedback we receive from the reactor, how can we improve the selectivity of the process. Good. The first example I want to make is the nitrogen cycle. So most of us are familiar with the nitrogen to ammonia conversion. That's the established catalytic reaction in the chemical industry to generate ammonia. But when you look at the nitrogen cycle, it is much more diverse than just nitrogen to ammonia. There are many different species, many different compounds that we can find in different exhaust gases, in wastewater, in many different sources that we use those, capture those, and convert those, turn it into something that we can use, such as nitrogenous fertilizers, such as ammonia, such as urea. And that's part of the work that we are doing, especially in collaboration with dairy farmers. So their wastewater is rich in nitrogen. And one of the technologies we are trying to develop is capturing the nitrogen in the dairy wastewater and turning it into ammonia, so that if in case that they want to grow corn next to their dairy farm, they don't have to store up oil ammonia from local or from centralized facilities, so they can make it on site. So that would be huge, because you're dealing with toxic compounds. So if you can reduce the transportation cost, if you can reduce the storage cost, that goes a long way for, especially for low-income farmers in Colorado.
I love it.
So we work with a variety of materials. As you can see, they're bell-shaped, structured nanomaterials. We call these plasmonic nanomaterials. These are specifically, they have specific features that when you expose them to light, they generate voltage. So I just mentioned that we want to use cheap electrons from solar energy to generate voltage, to get the voltage to run for electrochemical reactors. But these materials, not only they're conductive, but also when you expose them to incident light, like sunlight, they generate voltage, so you can save some of the voltage you need to drive chemical reactions. So that's pretty interesting in our research group to focus and pursue. And we have expertise, we have a patented technology on designing and synthesizing these type of catalysts. Especially these are hybrid because we mix different metals. And in catalytic reactions, it's rare that you focus on one catalyst and it does the job. So you have to mix different metals, different transition metals, and each try to contribute to one single reaction. These are, if you think about the chain reaction to ultimately get the desired product, these hybrid or bifunctional catalyst materials helps you to get to the desired product, but each contributing to a single chain reaction or single reaction in the chain process. And this is the example of palladium silver nanoparticles placed around the silver shell. We've also tested these catalysts with off-the-shelf catalysts from different vendors, and these catalysts have very high surface area, so around 4 times to 5 times higher surface area than the off-the-shelf catalyst. So when you have higher surface area, that means that your reactant acidity for catalyst, so you're enhancing the rate of chemical transformation just because you have more active sites for catalytic reaction. And the focus, we talk with industry every day, and we talk about some of the precious metals, especially the fuel industry we use, platinum, ruthenium, iridium, and when you talk about these type of metals, they quickly walk away. So one motivation for them is actually we can design some of these catalyst materials at the single atom scale. So single atom is, one catalyst is the size of one atom. It's very small. So that means that you're decreasing the amount of catalyst we need to run the chemical reaction significantly, and that means that you're decreasing your CapEx. So one of the problems, for example, with PEM electrolyzer right now is the use of precious metals, and that increases the CapEx significantly, and that's why we in the commercialization, one of the biggest barriers we are facing is the cost of these precious metals. If any way we can somehow decrease the cost of those precious metals, then we can find it's pretty much proportional to the total capital cost, so we can decrease the capital cost. The free market. So it's a quick example of the nitrogen cycle. There's ammonia synthesis. Part of the work I did in my previous research program is I talked about thermochemical reactors, a chemical process, burning natural gas, making ammonia. But this system really has 2 sides. So we have, similar to batteries, anode and cathode. And on the cathode side, essentially, you're turning nitrogen into ammonia in the electrochemical process. And where do we get our hydrogen source? The hydrogen source coming from water. So we split water, we get those protons. So water is H2O, so it has 2 protons, 1 oxygen. We get the protons from water, combine that with nitrogen in an electrochemical process. What we see on the left-hand side of these 2 cups, on the right-hand side, we essentially get the protons. Protons are transported across the membrane, the polymer membrane we have, separates the 2 compartments, and then on the left-hand side, essentially, you combine nitrogen with protons to generate ammonia. And again, as I said, we can use solar. These are light responsive. Upon exposure to sunlight, they generate voltage. And again, you save the amount, the total voltage that you need to run these electrochemical reactors. So the major challenge, why no one has studied this or no one has commercialized this process. So again, when you compare these technologies with incumbent technologies, you want to design this in a way that it has high yield, high efficiency, and eventually the cost of making this process, the cost of making ammonia in this process should be cheaper than otherwise, because otherwise your customers won't be very happy about that. Right. Okay. And another aspect of this is when we want to, these are gas-based electrochemical reactors, so these are the flow fields. So you're introducing nitrogen. On the other side, you're introducing, so you see there are two sides. On the other side, you're introducing hydrogen. And then in the electrochemical process, or instead of hydrogen, you also can use water later. So that's another interesting feedstock that we are exploring. And then the electrochemical process, the output of, so you have two inlets, two outlets. The outlet of the cathode side, or the negative side of the negative electrode, is ammonia. And you see on the right hand side, the top right, this figure that we are coating these catalysts on the polymer membrane, and we coat it on both sides. We call these sandwich type reactors because we have all these components and then assembled all these components so they look like similar to this. We have two electrodes and two compartments to introduce our gaseous feedstock, in this case hydrogen and nitrogen. And you might see one side is dark, the other side, which is the bottom right figure, is the transparent one. It's transparent intentionally just because we can expose them to light. In fact, you might see some of the solar simulators that we've been testing in the lab environment. So that solar simulator simulates exactly the intensity of the sunlight on Earth, which is 100 milliwatt per square centimeter. And we focus a lot on designing this, especially for CO2 conversion process. You're looking at flow cell versus membrane electrode assembly cell, and these are important, especially if you're, for example, want to capture CO2 and then convert that CO2 to your desired product, namely ethanol. So we have to flow liquid electrolytes, in this case potassium hydroxide, so we can capture CO2 and then convert that to methanol. So in the flow cell, that's the flow cell we want. These are the liquid compartments. And from this compartment, we introduce CO2 on the negative electrode. NEA cells, they're again gas-phase type reactors. We just introduce carbon dioxide and hydrogen on both sides. So on one side, you introduce CO2, on the other side, you introduce hydrogen, and you get your protons. You essentially try to protonate or hydrogenate carbon dioxide to generate your products. And at the powerhouse, we're looking at the largest scale. So this is just the example of that. You can see what we test at the lab scale and compare that to the largest scale system that we recently fabricated. And we are about to test this largest scale reactor. But that's the vision we have. We designed these catalyst materials. We tested at this smallest scale reactor. But once we successfully demonstrate at the smallest scale, we would like to also test it at the largest scale to see how much we can maintain the performance, the selectivity, the efficiency of the electrocatalytic process. And so this is the example of some of the testing we've done. I don't want to go through the details, but just want to say that we are testing how many of those electrons we can convert to desired products, what's the energy efficiency of the process, or how much energy could we need to make a ton of ammonia or a kilogram of ammonia, and then convert that. This is the stability testing. So what we want to do is the y-axis is current density and x-axis is time. So you want to make these systems as stable as possible. So you don't want to run for 1, 5, 10 hours. You hopefully want to run tens of thousands of hours, and also at high current density. So as you increase the current density, which in this case 600 milliamp, just to give you the background, water electrolyzer, commercial water electrolyzer run at 1,000 milliamp per square centimeter. So we have some room for improvement to get to the commercial water electrolyzer current density, operating current density. but also we want to improve. We are very happy that for 100 hours test under potassium hydroxide, we don't see any noticeable degradation, but we also want to run it next time for 1,000 hours, and then eventually run it for even longer time for the, on one of our largest scale electrochemical reactors. That should be
Expanding.
Speaking of incumbent technology, so this is where Haber-Bosch, the incumbent technology for ammonia synthesis, is that the hash line for energy input and also the energy efficiency. So for one of our cases, at the low potential region, about negative 0, saving point or 1 goal, we are competing, we are able to even beat the Haber-Bosch incumbent technologies with low current density, but it's very encouraging that it's still better than Haber-Bosch process for ammonia synthesis. But what we want to focus on, we don't want to compete in terms of size with Haber-Bosch. We want to promote this idea that we can have these reactors decentralized, modular, so we remove the transportation costs. Instead of having one giant Haber-Bosch power plant, we can have thousands of these small scale reactors. Every single farm can leverage these reactors and make their own fertilizer. So that's the goal we have. And by removing the transportation costs, insurance costs, storage costs, we are hoping even so we might not be able to compete with Haber-Bosch in production, but by removing all those extra costs that Haber-Bosch has to bear, we are hoping to compete with Haber-Bosch, and that this would be ideal or promising option for low-cost farmers. Oh. And we've seen the stability before and after, and we haven't seen significant degradation, but this is again 100 hours, and we want to run it for much longer time to make sure. In our business model, we are hoping that the catalyst replacement take place every year, so annually we replace, and that would be part of our maintenance cost.
You're going with
So the last, because we started late, so maybe still want to finish at 8 or I do want to. Okay. I just want to quickly talk about water, and especially we are living in Colorado, water scarcity. You might be, I'm sure you're all familiar with how much water stress regions we have around us, and especially this impacts our farmers significantly for growing crops, for dairy farm. We've been talking to many dairy farmers that the major point is access to water right now in their operation. And think about how to treat wastewater, how to, I talked about circular nitrogen economy, but again, we can focus on water economy, circular water economy. Reuse one of the wastewaters we have from different sources, and especially since most of our power plants unfortunately getting obsolete, so the maintenance cost to keep these facilities up and running is enormous. So thinking about modular systems, electrifying systems, again, the smallest scale, decentralized, that you don't need a giant power plant. You need a smallest scale system to treat, for example, the wastewater from a single dairy farm or the corn farmer. And that's the goal. If you look at some of the wastewater sources on the right-hand side, if we design a system can take those waters and again get another life, bring another life to those waters, that would be very significant for especially this region that we live. In Colorado, I'm sure you're familiar, water transport is significant, but in Colorado especially it would be very exciting to focus on this decentralized water treatment system, just because 80% of the population lives on one part of the state, and 80% of the water sources are on the other side of the state. So because of this, it would be very interesting to think about these decentralized modular systems to treat water locally. Right. But it's a challenging topic and challenging project, just because water contains too many contaminants, too many compounds that might foul your electrodes, might contaminate your system,
like degrade your catalyst. So designing these electrode materials that can potentially withstand these harsh conditions with all these chemicals, compounds, it's critical. And that's one of the projects we are currently focusing on. One example is PFAS. They call these forever chemicals just because it's very hard to degrade PFAS compounds from plastics, from all over the chemical industry that they're using. It's very hard to degrade these compounds. And one of the projects we are pursuing in collaboration with one of the waters, our industry partner in the wastewater treatment, is designing these electrode materials that can degrade PFAS with very high selectivity. And as I said, when you look at the potential, because in the electrochemical systems, you're trying to find a sweet spot that you can degrade some of these compounds with very high selectivity. And you look at all these aluminum, nickel, iron, manganese, calcium, even lithium, you really have a very narrow region right here that you can play around with in order to enhance the rate of chemical reactions if you're not looking to degrade those compounds. But we really can, this is the region that basically we can't just stay on that, we can rely on that to run our chemical reactions. So we have to deal with all these cations, nickel, iron, aluminum, and how can we maintain the selectivity of the process at the presence of these compounds is what we are looking for. Because without having these compounds, it's so easy to get very high selectivity, but the question is, if we have in the real wastewater, that's not the case. So how can we have these compounds in the wastewater and then getting very high selectivity? And that's the example. This is Morning Fresh Dairy Farm. We are collaborating with them, and hopefully we'll be demonstrating a pilot system at this dairy farm around 15 miles from Fort Collins. This is basically the wastewater that they're storing in there because it smells so bad and it's a lot of nitrogen, which is, we talk a lot about carbon, but the amount of the nitrogen is very, especially in Colorado, we are advocating for renewable energy. It doesn't look very good to have these things in. Most of our dairy farms look like this in Colorado. The amount of nitrogen that they emit to the environment, it would be, for one nitrogen would be, especially this would be in the form of nitrous oxide, so it would be 273 times more harmful than CO2. So we talk a lot about CO2, but the amount of nitrogen just this emits to the environment is much harmful than the total amount of CO2 that this dairy farm emits to the environment. And again, they're very struggling with the amount of water they're using. So if we can treat that water, that dirty water that you see, black water or brown water, we can again treat that water in a way that most likely would not be suitable for drinking. But again, they can use it in their dairy operation, and that saves a lot of money in water, and also saves the environment, and also positively impacts the environment. So one of the projects, and we thought we can use this water. This water is full of nitrogen. We've tested this water, and we've analyzed this water in our professional analytical chemistry lab. We realized it's full of ammonia, it's full of nitrate and nitrite. And we thought we could take this water, and it has all those compounds that I said initially, that we can towel the electrode, and they create our catalysts. So we want to have a pre-treatment steps to kick out all those problematic compounds, and then capture, on the second step, capture the nitrogen in this scar and turn it into fertilizer. So they can use it they have a corn farm next to this dairy farm right now, and they can use that fertilizer for growing corn. And this is the example we've successfully demonstrated that the lab scale we can very selectively convert nitrate to either nitrogen. Some environmental engineers can be advocating to convert nitrate is a
pollutant. It causes many different problems, cancer, blue baby syndrome, and degrading that nitrate in the wastewater is critical. Some environmental engineers advocating to turn that nitrate into nitrogen. We've done that successfully, but what we want to focus on right now is turning nitrate into ammonia, just because ammonia is very much useful than just nitrogen. This is some of the modeling work, because we do a lot of experiments. My lab primarily focuses on designing these experiments, developing these reactors. But it's always critical to come back, do some theory, and understand what's exactly happening in the reactor. Do we have any opportunities to optimize our reactor by doing some of the calculations, some of the modeling work that we can leverage to optimize our system? And I have a PhD student primarily focusing on this system and how to optimize the electrolysis set. Essentially, reduce the potential losses, improve the energy efficiency of the process. And we've done a lot of work. When you look at these electrochemical reactors, you have many different losses. You have losses associated with the catalyst. You have losses associated with the electrolyte, the migration of ions from one electrode to the other, and how to optimize and understand these losses. What would be the major source of loss? And that would be one of the questions we would like to answer. Catalyst, electrode potential, and how to be decide the distance between these two. Essentially, these are some of the concepts you're exploring. And then being in electrochemical system, we have this significant pH change. We have two electrode systems, and we have many different reactions taking place next to these electrode surfaces. And one of the focus areas here is understand how the pH changes along the reaction or along the reactor in the electrolyte system. And that's the modeling work you see on the right-hand side. You're trying to audit the pH near the electrode surfaces. So the red is essentially when it turns and makes the positive electrode or anode immediately turns into acidic, and the negative electrode or cathode on the left-hand side immediately turns to blue or alkaline for basic conditions. And how do we control that? Is by we can use a laminar flow or turbulent flow versus laminar flow, so we can have some control knobs in order to control the pH. And also use the membrane. So membrane, the physical barriers between these two electrodes really help us to not only separate the products on both sides, especially if you're making hydrogen on one side, the other side is oxygen. Combining hydrogen and oxygen, it's combustion, it's explosive. So we want to use a barrier to separate these two reactions taking place on two electrodes. And then how to optimize the energy efficiency of this electrochemical process by using membrane and without using the membrane. And it's interesting initially because membrane imposes some resistance to the overall cell. So initially, the cell without membrane has higher efficiency. But as you allow some time to the electrochemical system, in this case, we've run that for 32 hours, you see the cell with membrane, you see a slight drop in the cell with membrane, but the cell without membrane, just because some of the products you're forming on one electrode, you're losing that on the other electrode just because they're both reactive, but with different charges. So you're essentially destroying the products you're forming on one electrode, not the other electrode. So it's important to use membranes in our cases. And lastly, I just want to discuss about the process of some of the process design you're doing for urea synthesis and methanol synthesis and DNA synthesis. So the diamethylene ether, it's one of the fields that we are very excited about. It's similar to methanol, but it's much more reactive. It has a property of diesel fuel, so it's very reactive fuel that we can use in our transportation and power generation systems. But it's hard to make electrochemically, and one of the projects we're pursuing right now is how to make dimethyl ether in that electrochemical process from CO2 and water. But also DME can be produced via dehydration of methanol. So if in an electrochemical process, you're able to make methanol, then you can dehydrate that by increasing the temperature. Then you're making DME from methanol. So either direct path or indirect path via methanol is one of the two pathways that we're exploring for DME synthesis. And for urea synthesis, we need nitrogen source. So urea is, in the industry, urea is directly produced from ammonia and CO2. So you have the nitrogen source, you have and also the carbons. Is we want to use CO2, carbon dioxide, and also any nitrogen sources we have out there. Can be air, can be nitrogen, can be nitrate, and combine that in our electrochemical process to make urea. So especially in the United States, it will be much promising because 49% of all nitrogen fertilizers used in the United States goes to urea. So it just because it's easy to store and basically apply to this field, urea is much more popular than ammonia. So we are thinking about generating urea in our electrochemical process. And these can be not necessarily, for example, for the case of DME, can be a tandem system. So you make CO carbon monoxide out of CO2, and then in the second reactor, you essentially combine that carbon monoxide with hydrogen or water to generate methanol, and then the next step would be dehydration of that methanol to make DME. Ideally, the holy grail would be here to just directly make DME, now without going through the dehydration, because dehydration also adds energy to your overall energy, total energy consumption of the whole chemical reaction. But also we're looking at making other fuels such as propane or renewable natural gas. There's some interest in power generation industry, especially if you're making renewable natural gas for them. Even so, for us, it's not very promising with respect to DME or methanol, but if you're talking to people at Excel, they'd be very happy to see that we are making renewable natural gas. And we have DOE collaborators really helping us to understand the catalyst. These are very sophisticated instrument and spectroscopy techniques that help us understand the behavior of our catalysts during the electrochemical reactions. And we have collaborators that we send our catalysts, and they can really help us understand and give us some feedback about the behavior of our catalysts in the electrochemical system. So pretty helpful information we can gain from these type of spectroscopy systems. And finally, doing some techno-economic analysis, I just want to show you some of the unit US dollar per gallon for some of the fuels we are hoping to make, DME, propane, and renewable natural gas. And you see for some of these fuels, I don't know what's the gas price today, but it's not very far off from what we pay today to fuel our car. And it seems that, and also think about the tax credit we can leverage or hydrogen recovery or carbon credit by adding all those. These economics would be very exciting to pursue in the future. For example, for DME, it would be very exciting to get to $500 per ton, and that would be this line. If you look at the x-axis, is the conversion process. We call this Faraday efficiency, so one is 100%. And on the y-axis, we have renewable electricity cost, which goes from 1 cent per kilowatt hour all the way to 10 cents, which is what you're hoping to get, especially in Colorado, 2 to 3 cents per kilowatt hour is not, it's pretty realistic, we believe, from solar and wind. And there's some regions, if we go to very high conversion process, potentially get 2 cents per kilowatt hour, we can get to $500 per ton. And that pretty much competes with the thermochemical reactor using the Fischer-Tropsch process that varies again fossil fuels. So I think I'll leave the conclusion of it. Thank you so much for your attention, and I think today get questions.
time. When I look at energy storage, it always looks like nothing beats chemical plants. That gives you the highest, most stable energy storage. Of these different fuels you've examined, which one do you think is closest to working as the
Right, that's a great question. Again, comes down to the how much cheaper you can access the renewable electricity, and because that's in our electrochemical system, 60 to 65% of the output goes to the actual power, the electricity power. And if that there's a thought, it makes a huge difference if you have access to 1 cent versus n cents. But some of these carbon-based fuels, ammonia is, especially if we can look at the local, again, very wastewater, capturing their nitrogen and turning it into ammonia or urea is very promising just because we might not be able to compete with incumbent technologies based on natural gas, but when we decrease the transportation cost, the storage cost, and thinking about, let's say, to have one module every single farm in Colorado, then we start to compete with the current price of basically fertilizers that farmers are paying. So for example, for ammonia, they're paying $800 per ton, and we think that we can offer them $600 to $500 to $600, which is pretty promising for some of these, especially low-income farmers, just because they can't launch fertilizers, pay much money for buying fertilizers, and for carbon-based fuels it can be also promising for making methanol. So methanol is one of the fuels that we think we can make with very high selectivity, and that's what they can be with featured throughout this process. And
So you talked a little bit about the capital expense for some of these things. So you're talking about saving, $100 a ton or a couple $100 a ton on how much capital do you have to invest to be able to make that kind of return? What's your ROI look like for that side of breed?
Right, we've done a lot of these calculations to just understand ROI for most of these processes, and we are hoping to reach ROI of 1 to 2 years, so average 1.5 years for most of these technologies, especially for ammonia synthesis. And the capex, these type of reactors cost somewhere between $30K to $50K, depends on the capacity you're looking for. And they're making about 200 metric tons of ammonia per year. And again, if you have a corn farm, about 1,000 acres farm, right now that you need about 50 metric tons of ammonia fertilizers. So one of these reactors, the for are about the average size of 1,000 acres, which is, again, for us would be very promising because the footprint for these reactors may be the size of one of these, maybe it's the size of that table over there, but so the footprint is not very large, and you can have it at the corner of your farm, making your own fertilizers and outbuy. And again, it would be 50 tons for Haber-Bosch is nothing, just because they want to go as high as they can to decrease the cap because of the economies of the scale. For Haber-Bosch, for us it's great just because we can focus on globalized, decentralized reactors so that we can just be one farm with our reactors.
Yeah, I agree. Being able to solve the transportation costs, I mean, one of this is a huge advantage in getting your ROI.
And also the storage, because right now farmers have to buy in bulk and store. But in these reactors, you can just switch it on, turn it off whenever it's needed, how much you need. So you don't have to make 50 tons in one just shot. So you can just make a couple of tons and then next month make a couple of tons. So this gradual production of chemicals, that eliminates also the storage costs of ammonia.
As long as you're talking now, this one follow-up there, are you looking at generating the power from that locally as well, or are you assuming straight power?
We wanted to use ammonia to power the tractor, so that's one of the ideas we will be talking to farmers, because ammonia, because of the hydrogen content, you can also burn ammonia similar to other types of fuels. Less energy, but at the same time, tractor don't need to be competitive to diesel or ammonia has 1/3 of the diesel energy content, but at the same time, we don't need too much power. You don't want to use it for primarily for off-road. So again, this ammonia is always we are excited with ammonia synthesis just because it's a multi-purpose commodity chemicals that you can use in the energy, transportation, power, and also obviously fertilizers.
So the small scale farm, dairy farms, how much additional solar cells, solar panels should be used to drive the swings?
Right, that's a great question, and we've been debating recently with our team members that how much solar are we better off to purchase a solar panel and just hook it up to our reactor and run the system? And it seems that the capex goes down because we can purchase solar panels and just get access to cheap electricity all around. So we don't have to pay the extra electricity price. And again, the footprint for this is for any reactors with a footprint of 1 meter by 1 meter by 1 meter, you essentially need 1/10 of that volume for the solar panel. So you essentially don't need, so the solar panel won't be your limiting factors to that. So the power won't be very significant in this case.
That includes, that includes a catalyst being able to self-generate some electricity in that case.
Yes, so the goal is you don't have to do it. It's nice if you can, so you can save some voltage, improve your energy efficiency, of course, but you don't have to. If you, for example, you're trying to run your system in a cloudy day, it's not the end of the world just because you still can use some of the power you can generate from other renewable sources that you have out there.
So this reactor, when you're making fertilizer, what things do you from the dairy waste that become essentially waste you have to give it?
Right. So what you want to do is these type of reactors, you pump wastewater that contains nitrogen, and then the output would be ammonia in the gaseous form that we condense and make it in the liquid, store it in the liquid form, and treated water. So these would be our products. So we can use that treated water, and we can use that fertilizer.
But what are your waste products? Like, do you get that extra salt that you have to get rid of?
So
Sludge.
maybe if you need pre-treatment, if it's very dirty, then we have to do pre-treatment, but I have to deal with the sludge. But we call this plain saline water. So it doesn't necessarily would be dangerous or detrimental for irrigation. Again, it would be tough for right now. They're using it part of this water for irrigation. So it seems that that quality of water we've seen, if they use it currently for irrigation, then that treated water shouldn't be a problem for growing crops. Thank you.
Kevin,
No tolerance, as you said, like the chemical reactors, intermittent electrical supply. I mean, could you just put a photovoltaic array on them and the clouds come over and the ratchet slows down and the clouds pass and it goes back up? Does that cause fouling or any problem with the cells, or can they just operate very intermittently?
Right, that's a great question. And one of the beauty of these reactors, because otherwise has to run stable, so it doesn't go up and down. These reactors can operate dynamically. So with the power supply, with whatever, like the cloud just don't have power, it goes, the turn on and turn off, it will be like in a couple of seconds. So pretty dynamic based on the power. I mean, of course, if you have less power, you get less chemicals, less output, but doesn't impact the system. The catalyst is still stable, the system is stable, so you basically follow pretty much the renewable supply. So the chemical products, the output, they pretty much follows the power supply that you provide to the system.
So we can use this to balance the grid. The grid's got extra power. We use 10 other more.
Right, absolutely. For DME, so that's one of the ideas we have with DME, that for peak shaving, we call it so that
exactly, hair, created it.
yeah.
Drag, growing my change, Steve, the bone, gosh, and stuff to make it something that podcast. The gears that you're working with and you're setting up a system, when will that be operational?
We are hoping that sometime later this year we can test our largest scale reactor. I have a photo of the reactor.
the one that we want to test at the bar so later this year.
Are you going to invite us over there?
And absolutely, they have a nice ice cream there, so
Yeah. Morning, sorry.
yes, there's point or so. They've treated us multiple times already, so we enjoy being there.
Not just things. Top of that you started off with energy storage, and I'm curious what that all chain looks like. And now you got hydrogen electrolyzer as part of it, very low efficiency, other steps, and then you got to get back to electricity heads. So your proposal, whether it's DME or ammonia or whatever skill you produce, what's your generation technology? And secondly, if it's high temperature combustion, it's going to produce ozone. We're not attain that. So,
And for ammonia, primarily, we're looking at solid oxide fuel cells. We have a project we want to demonstrate in Hawaii, and they got enough solar power, and we are hoping to make capture their nitrogen in the base water, turn it into ammonia, and then use solid oxide fuel cells. So we don't, as you said, combustion and gas turbine. It's possible, but makes a lot of NOx. We want to mitigate that. One idea would be to use solid oxide fuel cells. Runs actually more efficient than gas turbine. Gas turbine is about 40-50% max efficiency. Solid oxide fuel cell, we can go up to 60% energy efficiency and doesn't use any NOx. That's the back to power. And of course, again, if you want to compete with batteries, short term would be tough to compete with just because very efficient lithium-ion batteries. But if you're looking at you want to make ammonia today and then turn it into power like 1 month from now, then SOFC or solid oxide fuel cell is a promising technology. You can store ammonia and then bring it back to power by using this.
You're saying there's such a thing as an ammonia fuel cell then?
Yes, it's naturally, yep. There's direct ammonia fuel cell.
Instead of combustion, because I heard combustion is very hard to control ammonia. Even try to make them ammonia endings unstable.
You have a very strong combustion there, and I tried to convince them to run their gas turbine with ammonia, but their major concern is making NOx, and it seems that it's very hard to control NOx, so we are now transitioning to ammonia fuel cells, so at least we know that we're not making any NOx in that system.
And
I think direct methanol fuel cells can be about efficiency.
Absolutely, that's very promising.
Are there DME fuel cells as well?
The properties are similar. Again, DME hasn't been explored significantly as a fuel. We have some niche markets for DME, but we think we can tune the system or basically repurpose the same methanol fuel cell to use it for DME because the properties are similar.
awesome. DME, are you targeting heavy trucks?
That's an awesome choice. Yep, that maybe you vehicles suspend because light duty we probably can't compete with electric vehicles, but for heavy duty medium vehicles, we still we are hoping we have some hope on hydrogen, but we think DME would be a great choice, especially if you make it from carbon dioxide. So you sort of have a circular system. You can bust the fuel, generate CO2, and then take that CO2 and turn it into fuel. And one of the ideas we have with our gas turbine at the powerhouse is exactly that. We burn natural gas in a gas turbine or whatever carbon-based fuel in a gas turbine, capture that carbon dioxide and turn it into fuel, and again burn that fuel in the gas turbine. That will sort of just enable this circular cycle.
Spending chunks. We have carbon dioxide of these people. And then doing this about me. Yeah.
all right, great.
There's no more questions. We can get to enough for a cake, but I